Hello everyone. Today we'll start magnetic field. Write down the heading. And in magnetic field, first we are interested in magnetic field of a current carrying wire. Write down the subheading. Magnetic field of a current carrying wire. And this magnetic field of a current carrying wire is studied under this Biot-Savart law. Biot-Savart law, magnetic field. Now, so far we have seen electrostatics. In electrostatics, charge was at rest, and you know that when a charge is at rest, it produces only electric field. Now, when I say magnetic field of a current carrying wire, this is the important part. Current. Current means we have a charge and this charge is moving. Rate of flow of charge is what? Electric current. And a moving charge produces both electric field as well as magnetic field. So the moment you have a current carrying wire, you will get magnetic field, but we do not get any electric field when we talk about a current carrying wire. Although I said when charge is moving, it produces both electric field as well as magnetic field. So who can tell me why we do not see electric field when we have a current carrying wire? If you think you know the answer, either you can switch on your mic or you can write your answer in the comment box. Let me repeat my question again. A static charge, in fact, do one thing, although we have written this thing in electrostatics, write down this part again. A static charge at rest. A static charge only produces electric field. Whereas a moving charge produces both electric field as well as magnetic field. This is the very beginning of electrostatics, the first class of electrostatics. We discussed this thing. So my question is, when you have a wire, and in this wire some current is flowing, that means charge is moving. then it only produces magnetic field, it doesn't produce electric field. Whereas the statement which you just saw, it says that a moving charge produces both electric field as well as magnetic field. So can you give me an answer? Why? Think about it. I'm giving you 20 seconds for it. No response. A wire is electrically neutral. It has negative electrons which are moving in this direction, opposite to the direction of current, but it also has static nucleus, positive charge which is present inside the nucleus. Positive charge which is static is only producing what? Electric field. Electrons which are moving, they are producing electric field as well as magnetic field, but electric field of negative charge is opposite to that of produced by the positive charge, and therefore the electric fields get cancelled. Now the only thing which survives is what? Magnetic field produced by moving electrons, and therefore we say that a current carrying wire only produces magnetic field. Write down this. A current carrying wire is electrically neutral, that is, it has same number of electrons and protons. It has same number of electrons and protons. Electrons are moving inside the bracket opposite to the direction of current flow, whereas protons are at rest, which means protons are only producing electric field, whereas electrons are producing both electric field as well as magnetic field. Now, electric field produced by positive protons is cancelled by the electric field of negative electrons, and therefore only magnetic field survives. I hope this concept is clear. Now, The magnetic field produced by a current carrying wire is formulated by these two Biot-Savart. This T is silent, Biot-Savart, and is given in this form. If you have a current carrying wire, look carefully and you take a very small segment DL. Look at this DL vector. This portion, this wire has an irregular shape. So when you will take a small segment DL, it will become a straight segment. This DL, which you see from its tail, if you choose a point and position of this point with respect to the tail of DL is R, which is kind of position vector. You don't have to worry about position vector and all. Simply from the tail join this point. It gives you the position of this point with respect to this DL. Then at this point, magnetic field, I hope you remember, magnetic field is presented by B. So the magnetic field which is being developed by the small DL segment is dB. It's a small segment and therefore its contribution in magnetic field is also very small, dB. When we will find magnetic field of the whole wire, we'll remove D. But right now, this dB, remember, is the magnetic field produced by a small DL element. This dB is mu naught upon 4 pi. What is mu naught? We'll discuss that. Mu naught upon 4 pi I dl cross R divided by R cube. If you have done this thing in your school, then you may have seen this, or you may have seen the simplified version, which is the magnitude part. We'll discuss that also. But this itself is an important question for any examination, board or competitive examination. Mu naught upon 4 pi I dl, this is cross. Cross means cross product R divided by R cube. Mu naught upon 4 pi, its value is 10 to the power minus 7. In electro, we were discussing epsilon 0, epsilon naught. Right here in magnetic field, it's mu naught. Epsilon had a name. It was permittivity of vacuum, epsilon. This mu naught is called permeability. Permeability of vacuum. Mu naught. Now, we discussed epsilon naught at the end of electrostatics. Similarly, as of now, you don't have to worry about what mu naught is. For you, mu naught upon 4 pi is just a constant, and this constant mu naught upon 4 pi has a value which is 10 to the power minus 7, and mu naught has a name which is called permeability of vacuum. How easily magnetic field lines can pass through a medium, this is something which is decided by this number. We'll see this thing in detail later. As of now, I told you, remember this thing as a constant. This part, don't forget to put this whole thing inside a boundary. It's an important result. You can mention like this. Now, let me see how comfortable you are with cross product and all, and then we'll go into the detail. Look at this. Look at dl and r. dv, which is coming from this, is the cross product of dl and r. dl and r. So right here, this dv get me direction of this magnetic field. What is the direction of dv? Up, down, right, left, towards r, away from r, perpendicular to r, in this direction, out, in. What do you think? Let me see. What is your knowledge about cross product? Go down this and try to answer this thing in the comment box. Everybody is writing perpendicular. Perpendicular to what? You cannot simply say perpendicular. Give me the reference that this thing is perpendicular to this. Well, only two answers are precise. Direction of dv is inwards, like this. This is about cross product. If you want to understand cross product in detail, just after the class send me a request and I will give you a lecture in which I have explained everything. But as of now, look here. This is dl vector. You can also draw this thing separately. This is r. Whenever they ask you cross product of two vectors, then direction of that cross product is always perpendicular, which most of you said initially, perpendicular. But perpendicular to what? That's what matters. So the cross product is perpendicular to the plane in which these both vectors are present. So this is the plane of the board. Perpendicular to the board is this arrow as well as this arrow. This is not perpendicular to the board. This is perpendicular to the board. Now there are two options. It can be out like this or it can be in like this. This is decided with the help of right hand. First it's dl, second it is r. Take your right hand and these fingers, they should be aligned with dl vector. This is something which you will need a lot in magnetic field, remember. Align your fingers or your palm with dl and then curl these fingers towards r like this. This curling is from dl to r using right hand. dl to r. Now this thumb is pointing inwards. I hope you can see the thumb is pointing in. Had it been r cross dl, then it should be like this. r dl, thumb is pointing out. I request you to practice this in your notebook. Align your fingers like this along dl vector. Make a curl. It should point in this form. Now, this curl, it tells you that dv, which is given by the thumb, is pointing inwards. Now, inward pointing vectors are shown with the help of a cross inside a circle. This cross means inwards. Or, as one of you wrote, minus k cap. If you say this is I cap, this is j cap, this is k, then what is in? Minus k cap. Write down this and then we'll write a statement. Write down the statement. dl vector is taken in the direction of current flow. dl vector is taken in the direction of current flow Next point, let's write down the whole thing in terms of points. R vector is the position vector. R vector is the position vector of that point. R vector is the position vector of that point where magnetic field is required. Inside the bracket, with respect to the tail of dl vector. If this is dl vector, this is the tail of dl vector. With respect to this tail, you will draw position vector. Next point, direction of magnetic field. Direction of magnetic field is perpendicular to both dl vector as well as r vector. That is, magnetic field is always perpendicular to the plane in which dl vector and r vector are present. And is given by its direction is given by right hand rule. According to right hand rule, right hand fingers should be curled. Right hand fingers should be curled from dl vector to r vector. Then thumb points in the direction of magnetic field. Then thumb points in the direction of magnetic field. Now, many a times people, they are confused in finding direction. When I ask them to take a curl, they do this kind of curling, this curling, this curling, this curling. They have no idea how to take a curl. So what you have written, this thumb, it gives you the direction of magnetic field. Now you cannot hold your thumb like this, because whatever is the direction of magnetic field, it is perpendicular to dl as well as r. This is perpendicular to dl, but it's not perpendicular to r. This is perpendicular to r, but it is not perpendicular to dl. So what is that which is perpendicular to both this or this? And therefore, always keep your thumb perpendicular to the plane of DL and R. You cannot hold your thumb like this. Either you have to hold your thumb in this manner or you have to hold your thumb like this. Now suppose you are holding your thumb like this, then you are curling from R to DL. But curling is required from DL to R. And this way there will be no confusion at all. We'll come back again to the direction part. We'll also develop second and third method for directions. But this is the most general method. This is coming from cross product. Any cross product, you always do the same thing. It's not about magnetic field. It's about any cross product. Now, let's first open this thing. Let's complete the magnitude version. We have got the direction and then we'll further develop direction part. dV. Look carefully, I have removed the arrow. If I have removed the arrow, that means I am interested only in the magnitude part, which is mu naught upon 4 pi I dl. I hope you remember how to open cross product. Magnitude of first vector, magnitude of second vector, sine of angle between dl and r. So this angle between dl and r is theta. This is theta, angle between dl and r. Sine, after sine, you need to have angle between these two vectors divided by this r cube. Now, r and r cube cancelled and it becomes mu naught upon 4 pi I dl sine theta divided by r square. Most of the time, this is sufficient for us. Most of the time. Mu naught upon 4 pi I dl sine theta upon r square. For direction, we'll take the help of right hand curve. This is good for understanding direction and as well as for some spatial questions. Note down this much. If you are comfortable with everything so far, then write down yes in the comment box. And if you have any doubt, then just mention your doubt. It can be anything. Magnitude part, direction part, anywhere if you have confusion, then you can simply tell me your confusion. What is your confusion in direction part? Okay, let me again discuss the direction part, but before that, write down a point for theta. Theta is angle between dl vector and r vector. Theta is angle between dl vector and r vector. And for finding theta, both vectors should be joined with their tails together. Why did I mention this point? Because sometimes people get confused when we go for vector sum. What we do, we take a vector and then on the head of first vector we place the tail of second vector. Just to avoid this confusion, whenever you need angle between two vectors, what do? You join them with their tails. This thing will give you what? Theta. Now, regarding direction, look here. This is the wire. For simplicity, I have taken a straight wire. Take a dl vector. These lines are just showing that dl vector is within these two boundaries. This is your dl vector. Now if I take a point over here, not like this, but like this. Current is flowing in this direction. dl should be always in the direction of current. This is the position vector of this point. Right here, I need direction of dv. Just give me the direction. What is the direction? In, out, up, down. What do you think? Write down in the comment box. And use whatever I have told you. How to hold your thumb, how to make a curl. Take care of these things and you can easily answer what is the direction of magnetic field. Let's see how many of you answer this. Only 4 5 have answered. Rest. What's the problem with you? Can't you curl your right hand? This is dl, this is r. So first thing, magnetic field, it will be perpendicular to dl and r both. Something like this. This is dl, this is r. Then if this red marker gives you magnetic field, it should be like this. I hope you can see it now. It should be like this or this, perpendicular to this plane. This or this. Now, for that we need what? Right hand. This is your right hand. Now, how should you hold your right hand? Fingers, they should point along DL, make them parallel to this DL vector, and then curl should be towards R. So this is the curl. Right hand curl. From DL to R. When you make a curl like this, thumb is pointing inwards. Inwards is this cross or in. You can use cross, you can use in, or you can use minus k cap, doesn't matter. Now, get me direction of magnetic field over here. If I take a point on this side, this is R for this new point. What is direction of magnetic field at this point? Write down the answer in the comment box. Good. This time direction is outwards. Curling should be from DL to R. DL to R. This is the curling. DL to R. And thumb is pointing out. If thumb is pointing out, then direction of magnetic field is dot. Dot inside a circle, it is giving us direction of magnetic field. Dot or simply outwards. Now I hope you can understand that if I am on this side of the wire, I hope you have drawn the whole thing. If you are anywhere on this side, if you go for this point, curl, thumb is in. So what is direction of magnetic field? In. If you are over here, this is DL, this is position vector, curl, in, magnetic field is in. If you are on this side, left side of the wire, then your curl is in this form. If you're on the right hand side, curl is in this form. Look at the change. If you're on this side, thumb is pointing out, so magnetic field is out, dot. Anywhere on this side, magnetic field is coming out. Anywhere on this side, magnetic field is going in. And if you have heard this statement, maybe in 10th or in 12th, that magnetic field lines, they always form a closed loop. So what this cross and this dot, it tells you that magnetic field line around this current carrying wire is making a closed loop. Now visualize this. If magnetic field line is making a closed loop, how will it look? On this side, magnetic field line is going in, and over here it is coming out. It's making a closed loop, and because of that closed loop, everywhere on this side you will find cross in. Everywhere on this side you will find dot, 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 that is out. Which gives us a much better method, which is the second method for the direction of magnetic field. What is that? Look at the second method and then we'll write the whole thing. Instead of taking curl and all, from now onwards, you can also use the second technique. Hold your right hand like this, thumb, this time thumb in the second method is pointing in the direction of current flow, like this. Rest of the fingers, let them point towards that side where you need magnetic field, over here. And then make a fold which is perpendicular to your palm. Not like this. This is not allowed. I hope you can see. It should not be like this. It should be perpendicular to your palm. This thing is perpendicular to your palm. So how do you find direction? Thumb over here, make a curl, make a fold. The moment you make a perpendicular fold, these fingers now, they give you what? Direction of magnetic field. For this side, same thing. Hold your right hand thumb in the direction of current, like this. Rest of the fingers towards that side where magnetic field is required, make a fold, in. Write down the second method. Second method for the direction of magnetic field. Second method for the direction of magnetic field. Place right hand thumb in the direction of current flow, and rest of the fingers towards that side where magnetic field is required. Rest of the fingers towards that side where magnetic field is required. Now, fold your fingers perpendicular to your palm. Fold your fingers perpendicular to your palm. These fingers now point in the direction of magnetic field. These fingers now point in the direction of magnetic field. Let's do some practice. And do participate in this thing, because let me tell you, this right hand rule and all these things, for next 2 months you will be dealing a lot with direction in this format. We have a current carrying wire and current is flowing like this. What is magnetic field over here? What is direction of magnetic field above the wire? Write down fast in the comment box. Good. Not like this. Not like this. Second method says thumb in the direction of current. Not like this. This is opposite to the direction of current. Thumb. Rest of the fingers towards that side where magnetic field is required. Now make a fold. Fold is pointing in and therefore magnetic field, its direction is cross or inwards or minus of k cap. In terms of unit vectors, I, j, k, but this is in and therefore minus k cap. Now the way you can expect questions in this direction part, write down a question. A horizontal current carrying wire, a horizontal current carrying wire is carrying current from north to south, is carrying current from north to south. Find out direction of magnetic field. Find out direction of magnetic field at a point which is directly above the wire. You have a current carrying wire and it is carrying current from north to south, directly above the wire. You need to find direction of magnetic field. Let's see how many of you can answer this question. Not a single answer is correct. Let me give you a hint. When I say north, south, up, down, then your answer should be in this form. Your answer should be east, west, north, south, up, down. There is no in or out now. In and out word for this type of given setup. So do what? Hold your pen in such a manner that it lies north to south. Then choose a point which is directly above it. Place your right hand thumb along the length of the pen. Press to the fingers towards that point where you need magnetic field. Make a curve and then see where these fingers are pointing. Everybody is answering inwards, outwards and all. But do as I say. Not a single correct answer. Look here. Well, that's how you draw north and south. This is north, this is south, this is east, and this is west. Question says current is flowing from north to south. This is the direction of current, I. When I say above the wire, this is the wire. Let me highlight this wire. This is your current carrying wire. And current is flowing from north to south, which is I. Now, if I say above, then this is not above. Wire, question itself is telling you, is in the horizontal plane. Now this board is not in the horizontal plane. This board is in the vertical plane. And when I teach you, I have to keep this board in the vertical plane. But your copy, your notebook is in the horizontal plane. Most probably, you're holding your copy like this. This is the horizontal plane. And wire is also carrying current in the horizontal plane. So do what? This north, south, west, east, forget about the board for the time being. This north, south, east, west, when you draw these things in horizontal plane, it's like this. This thing is this. Now, current is flowing from north to south, and therefore hold your wire like this. Remember, this end is north, this is south, and the whole setup is in the horizontal plane. So current is flowing towards you can say. If this is the direction of current, I don't know if you can see the dot. Let me keep the gap on. So this is the direction of current. This blue marker, if you can see the color, gives you the current carrying wire. Above the wire, over here, somewhere at this position. Now somewhere at this position, how do you find direction of magnetic field? Right hand. Right hand thumb should point in the direction of current flow. This thumb, look at the alignment. Look at the alignment if you can. This thumb is pointing from north to south. Rest of the fingers towards that side where field is required, above the wire. Now fold. Make a perpendicular fold. Look at these fingers. They are pointing this side. What is this side? This is east. This is west. So the correct answer is direction of magnetic field is west. Let me see how many of you understand this thing in first attempt. I'll again repeat as usual, but let me see how many of you got west. If you understand it, then write down yes in the comment box. And it's a good thing one of you answered west also. Those who did not write west, if they understand it, then write down yes. If you are confused, write down no. Now, let me repeat the whole thing again. This setup of current carrying wire, which is in the horizontal plane, and this point, the point which shows the position where field is required. Let me show this thing with the help of this red marker. So top of the red marker, this top, it shows that point where magnetic field is required. This is the current carrying wire. If I have to draw this thing in this plane, then it will look like this. This is the look of your copy. This is the look when I present things on the board. This is the point which lies above the wire. This is above. Now I need field over here. If I need field over here, what will I do? Thumb in the direction of current, and I need field over here. This is the position where I need the field. Thumb over here, fold. Look at the fold. Fold is pointing towards west. Now, let's answer this thing with the help of dl cross r. We don't have to worry about mu naught upon 4 pi and all. They will give you the magnitude part. Direction is coming from dl cross r. The second method, if you are comfortable with cross, how easy it becomes to answer these things. Look here. So direction of magnetic field can be decided with the help of dl cross r. We are interested only in the direction part. What is dl? dl is in the direction of current flow. What is this direction? Minus j cap. Now remember, I am only interested in what? Direction, and therefore I am taking j cap, k cap, I cap only. Cross. What is r? R was this point over here. So this is r. What is this? K cap. So if you know what minus of j cross k is, if you know what minus of j cross k is, it will give you direction of magnetic field. Remember, equal sign is not for magnitude, it's being used for direction only. Direction part. Now I hope you know what j cross k is. J cross k is I cap, and you have a minus I. What is this? Minus I, and therefore cross product also helps you in finding the direction part. If your visualization is good in 3D, you will find magnetic field very easy. If not, then I request you to develop this type of thing. How to present something which is in 3D with the help of 2D. Well, you have to use your notebook, and notebook is what? A two-dimensional plane. But everything is what? Three-dimensional. This is the plane, and I need magnetic field over here which is pointing in this direction. With charges and all, things were quite easy. You had a charge. If charge was positive, electric field at any point is away. You can draw things in a single plane. That's how you provided electric field. If it's a negative charge, towards. But for magnetic field, things are a bit three-dimensional. So you have a wire. This is the direction of current. You will understand 3D in this form. Current carrying wire. I need magnetic field above the wire over here, and it is pointing in this direction. That's what is happening. This is a 3D. Look at this 3D part. But the most efficient method is what? Thumb. Over here, curl. You got the answer. Let's see if you are comfortable with this or not. Write down next question. A current carrying wire is placed horizontally and is current in it is flowing from east to west, and current in it is flowing from east to west. Find out direction of magnetic field at a point just below the wire. Find out direction of magnetic field at a point which lies just below the wire. Let's see how many of you present the answer. You can verify your answer with the help of cross. Whatever answer you produce, you can always verify that. This time current is flowing from east to west, I. This is north, south. When I say below, I'm not talking about this. This is the horizontal plane. This is your wire. This is north and south. This thing is in the horizontal plane. Current is flowing from east to west. It's shown with the help of this. This marker is for north and south. So remember, this is the wire. Just below the wire, down here, I need magnetic field over here. Thumb in the direction of current, but I need field over here. Your thumb should point in this direction. If thumb is pointing in this direction, make a curl, fold. Now I'm removing this so that you can see it comfortably. Thumb is aligned with the current. Rest of the fingers towards that side where I need magnetic field. Down, over here. This is your wire. Fold. What is this? What was this? This was north. This is what? South. And therefore, this time your answer is magnetic field is pointing south. You can always take help of this. What is DL? This in the direction of current minus I cap. Cross. Now everything is in the, keep everything in the actual horizontal plane to avoid confusion. That's your wire. This is your north south right here. So if I need field over here for this particular setup, I cap minus I cap, J minus J minus K, K. Again, forget about this. The actual horizontal plane, something which you see in your copy. East, west, current is flowing like this. South, north direction. Right here, below the wire, somewhere here. So this is I, this is J, out is K. So what is this position? What is R? Minus of J. Minus of J. Minus minus plus. What is I cross J? K cap. In this setup, this is your wire. This was north and south. This was the position for the point where field is required. Right here, field is coming K cap. What is K? This. What is this? South. So this K cap now in the actual setup is south. But avoid this. Take help of, this is the wire. You don't have to take these three markers and everything. In just one line you can find your answer. north-south current. Where is up? In this plane, this is up. This is the horizontal plane. Directions are in the horizontal plane. North, south, west, east, they take place in the horizontal plane. So this is the horizontal plane. This is up, that is down, below the wire. So keep your thumb like this in the direction of current. Where do you need the magnetic field? Inside, at inside point. Rest of the fingers, they're like this, they're pointing in. Now, make a fold. Look at the fold. It is giving you straight away south. Put on this and then you can leave. Thank you.